Okay, so some people, they see proteomics as a black box. They put an input and they get an output, okay? Or what is the same, they put a sample and they expect some results. So you are here to learn about this proteomics workflow, which I think at the end of the week you will know a lot. But there is another important point, which is the sample. So proteomics is not magic. So if your sample is bad, your results are going to be bad. So it's very important what you're doing with the mass spectrometer, the workflow you apply, how you analyze the data, but the most important thing is the sample that you are analyzing. So if the sample is garbage, you are going to obtain garbage as results. So in here, we will try to explain a bit different critical steps of sample preparation. One of them is the sample digestion. The other is sample fractionation. And also, at the end, I will talk a bit about quality control, which is also super important. Okay, sample digestion. So we are here in the beginning of the proteomics workflow. We have a sample, and we want to digest them, the proteins, into peptides. So why we don't work with proteins instead of peptides? Well, for different reasons, mainly technological reasons. So it could be better, in theory, to work with proteins because they have more information. But the sensitivity at the protein level is much lower. And also, now we have been working in peptide fragmentation. You have seen how complex an MS spectrum of a peptide can be. When we are talking about proteins, then it becomes much worse. So, but they are mainly technological reasons, as I'm saying. So probably in the future, when the instruments are better, more sensitive, and the fragmentation is improved, we will work with proteins. But until now, we are still, most of the people are still working at the peptide level. Okay? And one of the main proteases is trypsin. As we have seen in the previous class, trypsin is very convenient because it generates peptides that are mostly double charged, and they have one charge in each of the streams of the peptides. Also, another good point of the trypsin is that we have, on average, one lysine or one arginine every 10 residues. So it makes that the tryptic peptides are in a reasonable size, from 10 to 20 residues normally. Also, trypsin is very efficient. It works really well. There are other enzymes that they don't work that well. And, well, the advantage that I was saying before, that you have peptides with two charges, one in each extreme of the peptide. But sometimes we don't want to use trypsin, because imagine that you use trypsin and you get this coverage, which is 80% coverage, which is very good. Coverage means how many peptides, how many percentage of the protein you are seeing. So we never see 100% of the protein. We see a percentage. 80% is super high. But maybe you're interested in a particular residue in here, which you know it's phosphorylated. So, and with trypsin, you get this. So what can you do? You can try other enzymes. The most common enzymes that are used instead of trypsin are this chymotrypsin that cuts after tryptophan, tyrosine, phenylalanine, and leucine, except if they are followed by proline. Glu-C, which cuts after glutamic. Lyc, which is very similar to trypsin, but only cuts after lysine, not after arginine. And then there is this other lys-N that instead of cutting after lysine, it cuts before lysine. And then the type of peptides that you get are this type. They are also double charged, but the two charges are in the same site of the peptide. Somebody can tell me which type of ions are we going to see in a lys-N peptide? the charge is going to be always in the N-terminal part, no? Because if we break in whatever position, the charge will be always here. So we are going to see only B. Okay? Okay, so to digest the proteins, we want them unfolded. Why? Because if not, the enzyme does not have place to cut. Okay? To make the cutting points available to the enzyme, we need to denaturate the protein. But we need to be careful because the denaturant that we use needs to be compatible with trypsin. If we put too much denaturant, we are going to denature also the trypsin, which is a protein, and it's not going to work. And we need also that the denaturant can be removed before the analysis with MS, because they are generally very incompatible with the analysis with mass spectrometry. Okay? So the most common denaturant that we use is urea, although you can use other salts like thiourea or guanidinium chloride. And sometimes, in some occasions, we use also SDS, which is a detergent, but we need to be very careful because when you analyze your sample, you cannot have any SDS. If you have SDS, deionization does not work at all. You don't see anything in the MS. Okay? The trypsin that we use is a special trypsin, which is called sequencing grade trypsin, which is modified by a reaction called radioactive methylation in order to minimize the autodigestion, because that trypsin also digests itself. So, and we don't want that this happens. We want that the trypsin digests other proteins. So we use the Promega one, which is the most commonly used in proteomics, although there are others that also works. And a typical buffer would be 0.1 molar ammonium bicarbonate and a concentration of urea less than 1 molar. Why less than 1 molar? Because if it's higher than 1 molar, the trypsin is denaturated, and it's not going to work. If you read some compatible buffers with trypsin, you will see that it can also work with a low percentage of SDS. But be careful, because this low percentage will allow the trypsin to work, but it will kill your signal in MS. Okay? So always be very careful with detergents. But trypsin, as I told you before, is very efficient, but it's not perfect. So sometimes trypsin forgets a position and it does not cut, although it should have cut. This is a representation of the most typical miscleavage position. If you see, of course, when the next residue is proline, it does not cut, but this is not supposed to cut after when it's KP or RP. And other prominent amino acids that are very easily skipped for trypsin is acidic residues like aspartic or glutamic. Why? Because a catalytic triade that it's in the catalytic center of the trypsin, it has an aspartic, and it can cause some electrostatic repulsion when the next residue is an acidic one. So a typical miscleavage position would be this KD or KE, or the same with arginine. So when we talk, we have talked about other proteases. We have talked about this lyc, which only cuts after lysine, but which is very often used in combination with trypsin. Why? Because, well, what you do is you first do a first step with lyc, and then you digest again with trypsin. So at the end, you have the same type of peptide that you would have had if you would have used only trypsin. But the big advantage is that this lyc is compatible with 4 molar urea. So you can have the proteins much more denatured, and then you significantly reduce the number of peptides that have miscleavage. So this is very common to use this combination of enzymes.
But then to use the trypsin, you dilute it? Or?
Yes, you dilute the urea, lower than 1 molar, and you use it. Okay, so also before the digestion, we used to reduce and alkylate the cysteine residues. We use reductive agents like DTT, it's one of the most common, to open the disulfide bonds, and then we alkylate them with alkylating reagents like, for example, this iodacetamide. Why do we do that? Well, first, because opening the disulfide bonds make the protein to be more open and more easily accessible by the trypsin. But also, if we have the disulfide bonds, we can have like an equilibrium between these two forms, making the sample more complex. So we want to have all the peptides in the same state. That's why we are irreversibly alkylating these cysteines. This is a thing that you need to take into account when you do a database search, because then you put always this carbamidomethylation of cysteines as fixed modification. So you know you have done this reaction, we know it's almost 100%, all your cysteines should be like this, carbamidomethylated. Okay, so this would be a general protocol. You do first a denaturation, then reduction and alkylation. You adjust the buffer, diluting if you need, because you're using trypsin or whatever, and then you add the enzyme. You have different types of digestions depending on where you do the digestion. If you have a gel band, you can digest the protein in the same gel, which we call the in-gel digestion. If you have it in solution, you can also digest the protein directly. And we also work a lot with this FASP digestion, which is filter-aided sample preparation, which it has several advantages. So in here, what we have is a molecular weight filter of 30,000. And the big advantage is that you can load the sample in 4% SDS, because then you filter and you can eliminate the SDS by filtering. Okay? This is especially convenient for very insoluble proteins, like, for example, brain tissues or liver tissues or membrane proteins that, you know, they are very hard to be dissolved in urea. You can try this protocol with SDS to dissolve better the proteins. During the digestion, it can happen different things. So one very typical thing that happens is that the methionine is oxidized because of the air, especially if you use the filter that you are putting air through the filter all the time. The oxidation of methionine is something very common. Another secondary reaction that can happen is this deamidation from asparagine to aspartic or from glutamine to glutamic. When glutamine is in the N-terminal, it can also easily form a cycle, which generating what we call a pyroglutamic. Okay? And also, if you use urea, you need to be very careful if you heat, because you can form this carbamylation, okay, which is this isocyanic acid that comes from the urea, especially when it's not very ready prepared, very fresh. It decomposes to this isocyanic acid, and it can react with a peptide to form this carbamylated peptide or protein. This is very bad because it modifies lysines, and then the trypsin is not going to work. You are not going to get anything out of your sample. So if you have urea, remember, do not heat. Never. Okay? You can heat up to 37 degrees, but not more. Well, these secondary reactions are important to know, because then you can include them in your search, because you know that this can happen, and then you take into consideration these modifications in order to interpret your spectrum. Okay, so it seems a minor subject, no? This thing of the digestion, it's easy. But it's easy, but there is a lot of work in digestions, even by very important people like Rudi Aversor, Albert Heck. they are publishing papers in the last 2 or 3 years talking about the digestion process. So it seems easy, but we need to pay attention, especially when you are doing quantification. It's very critical, the digestion. So here are some examples of articles. Even we have done one article about digestions. So as I told you, it seems a minor thing, but you need to be careful and optimize your sample and your digestion in order to get good results. Okay, so let's move to sample fractionation. So we are a bit more advanced in the workflow. We have explained this part, and now we are in here, still before the sample goes into the mass spectrometer. So why do we need to fractionate? This is one question. Okay, so in the human being, we have 20,000 genes that can form 100,000 proteins that can generate millions of peptides. In a 2 hours LC-MS-MS run, we get like 80,000 MS-MS spectrum. Not all of them are useful because some of them are redundant, or some of them are from the background noise. So with these numbers, we don't have enough to identify these millions of peptides that we can have in our sample. So that's why we need to separate our sample in more simple samples. Nowadays, the proteomics techniques that we have available, they cannot cope with a very complex mixer like a human, or for example, in the case of plasma or body fluids, the dynamic range is huge. Okay, you have 8 orders of magnitude, 8 to 10 orders of magnitude. And the dynamic range of a mass spectrometer is 4 to 5 orders of magnitude. So it's impossible that in one single run, we can identify all the proteins that are in plasma or in CSF. Okay? So this is why, then when do we fractionate? Of course, we fractionate, as you have seen this morning in the instrument room, before the instrument. So this is almost always. We have a chromatography, and we mainly use this reverse phase chromatography in an online setup to obtain these chromatograms that we have seen in the previous exercise. Okay? But for very complex samples, we do an offline, or it can be also online, but we mostly do it offline. We have one sample, and we generate different fractions, and each of these fractions is then injected into the online setup. And then it's how. How do we fractionate? We can fractionate by chromatography, by electrophoresis, or we can do also a depletion. Chromatography, I think most of you know what is chromatography. It's a method of separation that distributes compounds between a stationary phase and a mobile phase. Okay? So this is the schema of a column. With a stationary phase, a reverse phase, which can be with different C18, C8, C4. And this is the mobile phase. Well, I think I'm going to skip this. Okay, so which types of chromatography can we use in proteomics? As we have been seeing before, reverse phase, also hydrophilic interactions, and also ion exchange. So the reverse phase chromatography is the most widely used in proteomics. The sample is loaded in low organic solvent, in a hydrophilic solvent, and the the stationary phase is hydrophobic. Okay? So the order of the elution of the peptides, it's related to the strength of the hydrophobic interactions with the stationary phase. Okay? The typical mobile phases in a reverse phase chromatography are as phase A is water, and as phase B is acetonitride. And the different stationary phase can be either C18, C8, or C4. This you have seen this morning, that when it's online, we use these small columns packed on silica. But this is when we do this online setup that we do for all the samples. We can use also reverse phase to fractionate before the mass spectrometry. But then we cannot use the same type of reverse phase, because then we are not going to have orthogonality. We want to separate in different properties. Okay? So, sorry. So one way of doing this is use reverse phase, but at high pH. Okay? The typical reverse phase is done at low pH, at acidic pH, but you can fractionate the samples using reverse phase at low pH. You need a special type of columns, but they are, this separation is pretty orthogonal, and it works really well. Another way of separate using chromatography is this ion exchange chromatography that you may have heard about it. It can be either anion exchange or cation exchange, depending if the stationary phase is positive or negative. And the peptides are eluted either with increasing concentrations of salts or increasing or decreasing pH. Another popular chromatography used as first step in separation is the HILIC chromatography, which is completely opposite to the reverse phase. So in this case, the stationary phase is hydrophilic, and the mobile phase is hydrophobic. Okay? These are different types of HILIC chromatography, which is mainly based in hydrogen bonding and also electrostatic interactions. Another way of separation is electrophoresis, which most of you know very well, so I'm not going to explain it. So the most typical way of separating is a monodimensional gel. You just run a gel, you cut a band, you do the gel digestion, and you run it in the LC. So this is a way of separation, because in here you're separating your proteins according to their molecular weight. There are other ways of doing this. There is gel-free, which is similar to a gel, but without the gel. It's in solution, and you apply a voltage, and you can also separate the proteins according to their size. Another type of electrophoresis, which is isoelectrofocusing. And I don't know, I'm not sure if some of you have ever done a 2D gel, in which in one dimension we have a separation by molecular weight, and in the other dimension it's a separation by PI. So this was very popular in proteomics some years ago. It's really it's not very popular nowadays because of several reasons. One of them is that doing these gels is very tedious and they are not very reproducible. But other techniques now, they have surpassed the efficiency of this separation. But it's still good for some applications. For example, if you work with isoforms, it can be very useful. And well, you know, you see the proteins at the protein level, which is something important also. It has some advantages, but as I'm saying, most of the people, they don't use it anymore. And another type of electrophoresis that is used is this capillary zone electrophoresis, which is also done at nanoscale as the chromatography that we do before the MS. And in fact, some instruments now, they come with this capillary zone electrophoresis in front of the instrument instead of the chromatography. So this is also a new tendency. And the other way of separating, which is not exactly a fractionation, but it's a depletion. As I told you before, the body fluids first, are very complex, but also are very useful for diagnostic, for prognostic, for treatment. They are very interesting material to work with, but we have this dynamic range problem in which we have proteins that are very abundant and proteins that are very low abundant, and we are usually interested in the ones that are very low abundant. So it's a problem, because if we were interested in these ones, there will be not any problem, but it's not the case. So what people do is they deplete the abundant proteins using columns of antibodies against these most abundant proteins. There are several types of columns. Some of them, they only remove albumin and IgG. Others, they remove the top 20 more abundant proteins in plasma. There are several combinations. But if you only remove these, you already gain a lot, because you are removing the ones that annoys more. Okay, until here the part of fractionation. And now we are going to continue with some overview, very short, very basic, just to make you conscious about this topic, which I think we all need to be aware of, which is the quality control that we need to do in our experiments. So as we have seen, if we put garbage, we will obtain garbage. So we need to do quality control to know at different levels, to know when we have a problem. The quality control needs to be done at the sample preparation level. How can we do this? For example, digesting in parallel different standards with our samples, or even spiking in standards in our sample, which we know which results do we have to get. We can need to have also a quality control at the chromatographic level. For doing that, we can use also standards that we know the retention time and the intensity that they should have, and the resolution and different parameters that we can measure to be sure that our chromatography is working. And of course, we need to monitor our instruments. This can be done with a specific tests for each instrument type, and also with standards, measuring the intensity of different standards that we know very well, and we know what are the results that we have to get. Okay? The thing is that the standards for quality control, they need to be adapted to the specific experimental design. So we cannot use the same standards for everything. If we are doing phosphorylation studies, we need to have a set of phosphopeptides to be used as a standard. And we need also a specific software to monitor the instrument performance. There has been some softwares published also during the last years. Probably the most popular is this Simpatico from the Karl Meckler group in Vienna, in which they monitor different parameters from the instrument during the time, and they have a web system which allows you to make some graphs and to know when you have a problem and try to do some troubleshooting of these problems. So again, we have this figure. What happens if at the end we have very bad results and we have done all these quality control steps? Then we can go back and see what has failed. If our sample or our chromatography or our mass spectrometry, we can fix it. And then if we have everything ready, we know everything is fine, we should obtain the wonderful results that we were expecting. Okay, and that's it. Have any question?
So how these standards, I mean, you always integrate some standard samples in your pipeline? Or?
Yes, we do. We always digest BSA. We use as control a lot, BSA, in parallel with all our samples. And in case of complex samples, we use an E. coli extract, which is commercial. So we know exactly the amount that we are using, and we can control very well the response we should have. Yeah.
So it's like an everyday schedule or?
Every day, yeah. And after each run in the MS, we always run a short BSA sample just to check that the instrument is working. Yeah, we care a lot about quality control.
But it's because of high standard here,
Not everybody does like us, but you know, we are a facility, we provide services to other people, so we need to be sure that what we give, it's right. You know, it's different if you are a research lab that, you know, have more place to play, you know. But in here, I mean, we need to give good results. And if we have bad results, we need to know why.
You didn't say anything about randomization?
Yes, you need to do that, but you will see this on Thursday during the statistical whatever class. Yeah, you have some experimental design in there, and you will see this, blocking and randomization.